Okay, I'm going to demo the shortest path with grid. I'm going to demo the shortest path in a grid with obstacle elimination. So here is the question prompt. So you're given an m by n integer matrix grid where each cell is either 0 or 1. 0 means it's empty, 1 means it's an obstacle, a wall. You can move up, down, left, right, so no diagonals, to an empty cell in one step. Return the minimum number of steps to walk from the upper left corner to the lower right corner, given that you can eliminate at most k obstacles. Okay. If it's not possible to find such a walk, return -1. Okay. So, all right. So let me start with an example. So let's say I have a grid that's really small, just 2 rows, 3 columns, and start in the top corner and in the bottom right corner. And let's say that there's a wall here, and 0 means I could go step through it. So let's say something like that. Actually, something like this. Okay, so that means that I probably would need to use breadth first search to kind of, in a layered approach, grow my my paths from the start outward until I hit the goal. And at each step, I want to find, I want to keep track of, for the row and column, what is the distance that I travel to get to that position. So how many steps it takes. And there's one additional part of this problem, which is you can actually eliminate some of these obstacles. For example, I could turn this 1 into, so let's say k obstacles. If k is 2, that means I can eliminate at most 2 of these obstacles. So I could essentially walk through this obstacle and turn it into a 0. But I need to keep track of how many wall breakers I use. Okay, so this looks like I could probably apply the breadth first search shortest path approach and then try to modify it so that it can handle removing k obstacles, where k is chosen when you call the function. So I think my approach is going to be implement the regular shortest path algorithm, and then I'll modify it to handle eliminating at most k obstacles. Okay, so the definition of this is shortest path, and it takes in a grid, and yeah, I'll just say k for a number of eliminations, and I'll handle that a bit later. So with breadth first search, you implement it with a queue, and so let's, from collections, import double-ended queue. Okay. And so essentially I want to be adding items to the queue, popping them off, and then when I pop off an item from the queue, I want to search its neighbors, up, down, left, right, see which ones are valid, and it's valid when it's within the grid dimensions, so it doesn't fall off the grid. It's valid if you haven't already visited and seen that position, because you don't want to keep revisiting the same position over and over. And it's also valid if it's empty, so it's not a wall. Okay, so I'm just going to take some notes. Iterate for the queue. Okay, when is, okay, find neighbors up, down, left, right. And also, when is a position valid? So there's 3 parts to that. Within the dimensions, within the grid, not yet visited, and not an obstacle. Okay. All right. So iterate from the queue. Okay. So let me make my queue. So my queue is going to be double-ended queue, and each element is actually going to be the number of steps taken up to that point, the distance traveled, as well as the state, right? And the state is going to be the rows and columns. So state is row, column, it's a tuple for the row and column position. And what else do I need? I need to keep track of the states that I've already visited, because I don't want to keep revisiting the same row column position. So visited set, visited states set is equal to a set. Okay, and so it's going to store the state, which is a tuple with row and column. Okay, so state is row and column, steps and state, where state is row and column. All right. Okay, and let's see. So the queue is going to be, I'm going to be looping through while the queue is not empty. So while queue steps state. In Python, this is how you can check that it's not empty. Then you're going to q.pop left. So first in, first out, you want to pop off the earliest inserted item, pop left, and it's going to be q steps state. What will it pop off? It will pop off the number of steps and also the state. All right. So, and notice I'm sort of writing this kind of building out the skeleton, so you'll notice that I will need to insert additional code to initialize all this above the while loop. But right now I'm trying to build out the skeleton of what I'm trying to do. So then the other thing is I want to mark as visited, right? So actually here I realize I can actually initialize my queue so that I can start looping through it. And I initialize it with the start position, which is the top left corner. So here I can say start steps is equal to 0, start state is equal to 0, column, row 0, column 0. And so I'm going to initialize my queue, so queue steps state dot append. So steps, start steps, and start state. Okay. Oops. All right. So next I want to also create my. Oh no, I already initialized that. Okay. All right. So every time in the loop, I'm going to pop off the earliest inserted item, the steps and state. I'm going to keep track that I've already visited that. So I'm going to say visited states set. I'm going to add this state. So now I know that I'm not going to backtrack on it again. Okay. And then for the neighbors, it's up, down, left, right. So for row, column, in, I'm going to make a list of tuples. So up, down, left, right. So up is row -1, same column. Down is row +1, same column. Left is row, column -1. And to the right is row, column +1. Okay, so for each of these neighbors, what will I do? I want to check that it's in bounds. So the three things, when is it valid? All right, so if it's in bounds, so that means that it's less than or equal to 0, greater than or equal to 0, and also less than the end. Okay, so I need to actually get the number of rows and the number of columns. So here, I can get the goal row and the goal column is equal to length of the grid is the number of rows, and so -1 because we start counting from 0, and number of columns is length of the one row of the grid. So the 0th row of the grid will get the length, and then again -1 because we start counting from 0. All right. So if row is between this and the goal row, and the column is also within range of, so between 0 and the goal column inclusive. Okay, and I'm just going to include, I'm just going to move on to the next row with this backslash. So this is still part of the if condition. So it's in the grid, not yet visited, so the row column not in visited states set, and so one more, not an obstacle. So that means I'm going to access the grid row column, and notice that I'm checking this after I've made sure that the R and C are within the bounds. So this way I know that when I do access grid at row column RC that it's valid. Okay. Okay. So is empty, right? So when that's the case, then what do? It's a valid neighbor. So I just want to get the number of steps. So new steps is steps +1, where steps is from the original row column, and now I'm looking to move one position either up, down, left, right, so I just increment the steps by 1. And the new state is equal to the row and column of this neighbor. Okay, and so once I'm done, I can append to the queue steps state dot append. And what do I append? I append the the tuple of the new steps and the new state. Okay? Yeah, just realized I need to append this as a tuple. Okay. All right, so now I've also gotten the position for the goal row and goal column. There's another thing that I need to actually check every time I pop off an item from the queue, which is I need to check if we reached the goal. Okay, and I guess we could actually check this right away. So even before we mark it as visited, we can check if we reached the goal. So when have we reached the goal? If row is equal to the goal row and the column is equal to the goal column, then we know we're at the bottom right. Okay, so all we need to do is then return the number of steps, the distance it took to get to this goal state. Right? And then once we return, then we're actually done. All right. But otherwise, we check our neighbors. When the neighbors are valid, we add them to the queue so that we can then, in order, keep popping off the queue until it's empty, but then filling out all the states and also the steps. Okay. All right. So I think end for loop here, end inner for loop here, and let's see, end while loop. Okay. So if we've exited the while loop and we haven't returned the goal state, then that means that we are not actually able to reach it. There might be just walls blocking it, so we can never reach it. So return -1, not found, goal not found. Okay. All right, so this is the basic shortest path algorithm. And now what I'll do is I'm going to modify it so that I can handle the obstacles. Okay. So with the obstacles, what you'll want to notice is that when you reach an obstacle, instead of just having to go around it, you can actually break that wall, so to speak, with a hammer. But you need to use up your hammers. So you start with K hammers. So I think what's important here is to realize that you want to keep track of your state, right, which is your position, row, column. But now your state's also going to include the number of eliminations you're allowed, the number of hammers you have remaining to break down walls. And that means that you could be in the same position, like this wall right here, and you could reach that in two different ways. So just hypothetically in this example, you could reach this one by going from the start to here, but technically you could also have a really roundabout way. This is probably, yeah. For example, you might go all the way down to the bottom middle item square and then move up here as well. I mean, in this case, you wouldn't really want to do that, but it's possible to do that. And it's possible that maybe you've eliminated another wall already. So I guess what I'm trying to say is that you could reach the same row column in different places, and after having broken down a different number of walls. And so you want to actually keep track of the number of eliminations that you have remaining, and that's part of your state, and it will be unique, even if it's the same row and column, but there's a different number of eliminations or hammers that you have remaining. Those are distinct states that you want to keep track of. Okay. All right, so let's see, how do we do this? So let's update the state. So now the state is also going to be the number of eliminations remaining. Okay. And so let's see, start state is 0, 0, row 0, column 0, and then K is the starting number of eliminations. Okay. And you don't have to change this, you're still adding the steps and the state, start state to the queue. And now the visited states, you want to keep track not just of the rows and columns, but also the number of eliminations remaining. Okay, so we'll see that a bit later. But here you pop the item off the queue as before. Oh right, so I need to actually grab the rows and columns. So row, column. So initially, before the eliminations detail, it would be row, column, would be from the state. And now I'm going to also include the number of eliminations. Okay. All right, check if we reach the goal. That's the same. And let's see, visited states. Oops, that should be an underscore. The state is the row, column, and number of eliminations. Okay. And then find neighbors. So let's see, that's the same. And then, okay, when is position valid? Okay, so it's valid if it's in the boundaries of the grid and it's not yet visited. So now the state that we're looking at is not just the row and column, but also the number of eliminations. Okay. All right, so here's what I need to change it, is that before I only did anything if the grid is empty, but now if there's a wall, it's actually possible to to break the wall if I have some hammers to break it with. So what I'm going to do is I'm just going to check the first two cases, which is checking if it's in the bounds and not yet visited. And then inside here, I'm going to check for the two cases. So if grid RC equals 1 is a wall, okay. So what do I do if it's a wall? Okay. Now, if the number of eliminations is greater than 0, then I could use it. Then new eliminations is equal to eliminations previously minus the one that I'm using now to break through this wall. Okay. Otherwise, this is when the eliminations is actually equal to 0. Can't break the wall. All right. So in that case, I can't break the wall, so this neighbor should not be added to the queue, so I'll just continue. Okay. All right. So if grid row column is 1 is a wall, okay. So that's the case when it's a wall. Else, well, let me just make it more explicit. So elif grid row column is empty, then in that case, the new eliminations is just the current eliminations because I don't need to use up a hammer to break down any walls. Okay, so now outside of all these if statements, this will remain the same. So new steps is just current steps plus 1 for moving up, down, left, right to the neighbor. The new state is the row, column, and the new eliminations, and that will either be set to be the same if we didn't need to use a hammer to break a wall, or it will be decremented by 1 if we did need to use a hammer to break through a wall. All right. So the new state, row, column, new elimination, and then append the new state. Okay, great. So I think that about does it. And I'll just kind of review to make sure that this makes sense. So if I have a queue, and the item it will take in will be the distance traveled steps and also the state, which is row, column, elimination. I initialize it starting at the top left corner with the full number of eliminations possible, number of hammers possible, and initialize the queue. Yeah, and then loop through the queue. So I'm going to pop things off. I'm going to check if we reach the goal and also mark as visited. Visit neighbors. Check if it's inbounds. Check if it's not yet visited, so we're not backtracking. And then when we reach a wall, what do? Well, if we have the ability to break through that wall, which is this case here, then we'll just use that special wall breaker, but then keep track of the fact that we used it. But there's also the possibility that we've used up all our wall breakers, and so in that case, we can't go through that wall. We'll just ignore that position. And then there's the usual case where the square is actually available for us to walk into, so we don't need to eliminate anything. Okay, and then so now we know we have a neighbor that we can add to the queue. We increment the steps, update the new state with the row, column, and new elimination. Okay, all right, I think that's it. So the runtime for this with shortest path is usually linear, so if it's an n by n, then it will visit each position once because I'm using the visited state set to make sure I don't backtrack. So if it's, so it's big O of n essentially for the runtime, and also in terms of space, I'm having a set that keeps track of all these states. So it will be actually more than m by n because it'll be m by n potentially, let's just conservatively say times k, because k is the number of states. So you can sort of imagine that our grid is a two-dimensional row and column, and the k, the number of eliminations, is sort of like if you're looking at a multiple-story building, or so just like a 3D cube with different x, y, z coordinates. So it's the space used for this might be m by n by k, and that's about it. Thanks for watching.